About buffers today and buffer regions. All pH curves have at least one region where the pH remains relatively constant despite the continuous addition of a titrant. So you saw this when you guys did your own lab, and when I do the first one for you kind of thing, you know, I added some sodium hydroxide, and then I tell you it's like, it's, you know, pH is 2. Then I added some more and it's pH is 2. I added some more and it's pH is 2, and you guys are just laughing. This is never going to change. 2, 2, 2, and then 2.1. You know, 2.1, 2.1, right? So that continuous addition doesn't change the pH because basically it's in that buffer region, we say. It is in that place where just that little bit of sodium hydroxide or that little bit of hydroxide that I add is getting neutralized out by the acid, basically. So it's not enough to completely change the pH range, all right? So that happens in what we call these buffering regions. These flat sections of the pH curve are known as buffering regions. These regions can be found where the titrant volume is halfway to the first equivalence point and halfway between equivalence points. There can only be 2 buffering regions, okay? So we're only going to worry about 2 buffering regions at most, all right? So I guess I better do this now, and I think I forgot to do this first class here. So look, if you had a graph that looks like, let's say, that. This here, okay, this is your equivalence point here. Halfway, right there, this is your buffering region. This up here is not your buffering region. That is not a buffering region up there. It's only between the first equivalent, before the first equivalence point and in between equivalence points. So if you had a polyprotic curve, right? Polyprotic curve, like, oops, that doesn't look very good, but polyprotic curve, there's your equivalence point, there's the equivalence point. This here is a buffering region. This here is a buffering region, okay, between equivalence points. That is not a buffering region, okay? So make sure you understand where the buffering regions are, yes? These regions can be found where the titrant volume is halfway to the first equivalence point. So we know how to find the first equivalence point. We've done that, right? The end point, the first end point. We've find the volume of that. Halfway to that is the buffering region, or basically I know for sure that that's the buffering area, right? So here's an example here for you guys. You guys are going to go ahead and do this right now very quickly. You're going to draw me a graph. You're going to find the initial pH. You're going to find the equivalence point, et cetera, for this graph. Make sure you draw an appropriate graph for this particular one, acetic acid and sodium hydroxide. Go. Catch up here so that I'm not too far behind here, because all right, so should start with an acid, of course, yes, because you have 50 milliliters of the acetic acid. Where you have the 50 milliliters in the bottom, of course, you're adding sodium hydroxide, so the pH should go up. So I'm going to have to do this at the bottom here because I'm not going to have enough room. So first of all, initial pH here. I would take my acetic acid in the bottom, and I'm going to react it with some water. And I'm going to get H3O plus and acetate CH3COO minus, aqueous. It is what, 0.10 molar? So X, all right? I can find, of course, the Ka value for this. So Ka is going to be X squared over 0.10 molar. X will turn out to be here. Let's see now. I don't think I have this copied, so I'm going to have to calculate. Maybe I do. Oh, yeah, I think maybe I do. No, I don't. Yeah, let me just do a quick calculation there for that. So, let's see. Acetic acid, where is that here? 1.8 times 10 to the negative 5. So, all said and done here, let's see, 1.8 times 10 to the negative 5 times 0.1. Take the square root, and I get 0.0013. And I'll take the negative log of that. And I should get 2.87, yes? As the initial pH. So right here, 2.87, yes? Okay? Correct? Yes? You should have that, yes? All right, next. Okay, now that's the initial pH. That's just the acetic acid sitting in the bottom of the beaker there. Now I'm going to start adding some hydroxide to it. So now I need to talk about how we're going to get to that first equivalence point. Well, the only equivalence point in this case, it's a monoprotic curve, yes? There's no polyprotic acid or polyprotic base there. So I'm going to take my acid, of course, and I'm going to react it with some sodium hydroxide. So my hydroxide here. Proton donor, proton acceptor, so I'm going to get some water here, of course, and some acid, or acetate, I should say. I can tell you right now that basically the pH of that equivalence point should be above 7, yes? I can tell you that right now because that is a weak base right here. So this is a weak base. I know for sure that whatever this is here, the pH is probably going to be greater than 7, whatever that happens to be. Okay, and once again, we could check it out on our data booklet and estimate if we needed to, but I can tell you right now it's above 7 somewhere. Let's see. As far as this question goes here, what did I say? I had 0.10 molar. How much sodium hydroxide do I have here? 0.10 molar. So 0.10 molar. I had 50 milliliters. Is that correct? 50 liters, which is 0.005 moles. Which of course reacts with 0.005 moles here, and the volume of course is, wouldn't you know, 0.050 liters is your equivalence point, yes? Okay, good? That's all stuff that you should be able to do by now, yes? Yeah, absolutely. We've done that a few times now. So 50 milliliters, that's your first equivalence point. If I was going to mark that on the graph, that would be right there. Okay, there is only one equivalence point because it's not a polyprotic curve, so there is only one there. All right? The buffering region in this case, since it's only a monoprotic curve, is right here, 25. And yes, it kind of goes around there, but I'm guaranteed at 25, that is in the buffering region. Okay? So that would be your buffering region in this particular case here. Remember, when you look at this, I can add, of course, well, that's actually the bottom one here, the acid, right? So I start with the acid, I'd add a little bit of OH. It's not enough to completely change it to those two things there. I add a little bit of OH, it gets neutralized out. I add a little bit of OH, it gets neutralized out. Basically what's happening here is, because remember, this is your acid, this is kind of your base here, right? Once I get to that special endpoint, I now have more of this, right? The base part, because I'm making the hydroxide ion concentrations going up, yes? So once I add enough hydroxide, I will completely turn it into this. But right now, I have basically equal amount of this and an equal amount of this right now, okay, in this equilibrium kind of system. At first, it's an equilibrium system, right? I add a little bit of OH, it neutralizes out with this to give me this and a little bit of that, okay? But it's still in that equilibrium system. It's going back and forth, back and forth. I add a little bit more OH, and it neutralizes itself out. That's why the pH isn't jumping up. It's still staying the same because it's neutralized out. I add a little bit more, and it neutralizes it out. I add a little bit too much now, and now what's happened is I've had too much of this, and now it's shoved the equilibrium that way, and now I've only got products, okay? So now I'm on this side here, and I basically have that weak base and that acid. I keep adding the hydroxide, and of course the pH will continue, well, it flattens out again at the top there, but that's not really the buffering region. But that's what's happening right here, right? So that's your buffering region right in there, all right? So we're going to talk about that now. When only 25 milliliters of sodium hydroxide has been added, half the CH3COOH remains unreacted. Look, go back to here for a second. We decided it takes 50 milliliters for it to react in a 1-to-1 ratio, right? That's the equivalence point. Look, right here, a little bit farther down. One of these reacts with one of these to give me one of those and one of those, right? And at 50 milliliters, that's when it's perfectly 1-to-1. Yes, that's the equivalence point. So what does that mean? Well, what if I only took 25 milliliters of this, right? If I only use 25 milliliters of this, how much of this is actually reacted? Half as much, right? So if I only have half as much here, that means the other half is in this form here, right? Because that's the equilibrium system we're starting with. Acetic acid with water gives me acetate, right? Ions. So that's what's happening, okay, there. We have equal amounts, basically. We have just as much here in this form as we have in this form, okay, when we kind of start out there, or when we're halfway, because we have half of what's required. If we have half the volume, we have half the amount, right? We have half as much. So that's what they're saying there, basically. When you only take 25 milliliters, you're only using half of the acetic acid, which means, of course, you have half of that acetate ion, okay? Remains unreacted. At this point, the titration, there's approximately equal amounts of both, all right? And that's the buffer system. A buffer is a mixture of a weak acid and its conjugate base in roughly equal proportions, all right? Buffers maintain a nearly constant pH for the system when small amounts of a strong acid or base are added or reacted. Now, it doesn't have to be, listen, it doesn't have to be the acid with a strong base. It might be the opposite. It might be, of course, the base with well, strong acid, or vice versa, right? So when we look at our system here, look what happens. If we add a little bit of hydroxide, which is what we looked at basically, that little bit of hydroxide reacts with this acid here, and you get basically those two things there, right? If you're talking about the acid, you need to react it with the base, okay? It neutralizes itself out. That's what a buffer system does. It neutralizes itself out. It takes that little bit of base that you added, and it basically puts it back into the equilibrium, okay? So if we're going to talk about the acid here, I'm going to react it with the hydroxide stuff. And eventually, right, the OH is neutralized by reacting it with the acid. If you want to talk about the CH3COO minus ion, we need to talk about the opposite. If we're going to talk about the base, then we have to react it with, of course, the acid in this case to neutralize that out, okay? So depending what you start with, if you're going to talk about the acid, you're going to use the base that goes, well, yeah, the base. If you're going to start with the base, you need to react it with the acid, okay? Because buffers really are neutralized out kind of thing, equilibrium, right? The added H3O plus is neutralized by the acetate ion. Buffers are important in many biological processes that require a specific pH value. Enzymes function optimally only within a narrow pH range. Human blood is buffered by H2 hydrogen carbonate and a hydrogen carbonate ion there. Buffer and H2PO4 minus and HPO42 minus buffer, and that helps keep blood near pH of 7.4. The pH of a buffer can be calculated using a Ka expression, so we're going to take a look at that here. Now, here's an example of a buffer solution. Now, it's going to say something about the fact that this is a buffer solution, and the first thing, of course, you'll notice is that you have two concentrations here to start with. All right. Now, you got a 0.238 molar hydrofluoric acid and a 0.251 sodium fluoride. What's really the two things that I need to worry about here? Yeah, the hydrofluoric acid and the F minus, yes? Buffers are a system made with the acid and its conjugate base, or the base and its conjugate acid, however you wish to do that. You can write down either one of those expressions, okay? So you have really two options here to figure this out, if you want to figure out the pH. Now listen, if I started with hydrofluoric acid, now remember, hydrofluoric acid, and I'll react that with some water. In water, you would have H3O plus and Fe, not Fe, F minus. Okay, so there is a buffer system. Basically, it's acid and its conjugate base. All right, I'm going to cheat a little bit here because I already have the Ka value written down for this one somewhere here. There it is. Okay, so you could start with that. Okay, do you have its acid and its conjugate base? Sure you do. Okay, HF and F minus. Some of you guys might be, well, how did I know to start with HF? Why don't I start with F minus, for example? Why didn't I choose F minus to start with and react that with water to give me H plus, proton donor, proton acceptor, right? So HF and hydroxide. Is that what's happening as well in the reverse direction, basically, or if you start with the base? Sure it is. Okay. Do you have the conjugate acid and or base and its conjugate acid? Sure. Okay. Either one of these is acceptable. You could use either one. Nothing wrong with either one of these. You'll get the same answer either way. But look, it says we can use Ka values to calculate the pH. Look, what's pH here? Right? Right here, yes? What's the pH of this system? Can I use Ka values? Ka value says what? Hydrofluoric acid. I know the breakup of hydrofluoric acid. Do I know the fluoride concentration from the question? Yeah, you do. I know this. I know this. I'm looking for this, right? And I know Ka. And remember, Ka, we haven't done this for a while, would be in this case here H3O plus, right? F minus, equilibrium law constant, yes, and HF. Okay. Could I figure out H3O plus based on Ka? Sure you can. Okay. So listen, I could do that, right? And that's what we're going to do. Could I do it with this one as well? What changes though if I'm going to use this equation? You have to use Kb because you're talking about the base now, yes? Right? So if I wanted to use this, could I use it? Sure you can. You could talk about Kb is, of course, the HF, which you have, the hydroxide, which I don't know, over the F minus, yes? So could I use that one? Sure you can. But listen, if you use Kb, what do you actually find in the first step there? You find what? POH, yes? Then you still got to convert that to pH, correct? So not only do you have to change it from Ka to Kb value, you also got to change it from POH to pH, right? So which one is going to be easier for you? Which one's going to be quicker? Always the acid's going to be quicker because you already have the Ka values for you. And when you go to figure out pH, you're always figuring it out of the hydronium ion. It's already there for you because all acids produce hydronium ions. So which one do you want to do? I strongly recommend you do the acid one every time when you're talking about buffers because it's way, way quicker. Okay? And that's what I'm going to do. Can you get the same answer either way? Absolutely you can. You'll get the exact same answer, I promise you. Okay. In fact, the next example I have here, I did mine with POH because that's what I decided to do just for fun. And I can show you that if you want, if you don't believe me. I did mine with POH, and I'll do it with pH on the board again because I think acids are just way easier. You'll see that it's going to be a lot quicker. Okay. So I'm actually going to get rid of this one here. Okay. Not saying that's necessarily bad or anything. Once again, Ka is H3O plus, which I don't know, F minus, and over HF here. Okay, Ka for this one here is 6.3 times 10 to the negative 4. I don't know that. F minus is a 0.251 molar, and of course HF is 0.238 molar. All right, so solving for x, what's the concentration of x going to be? Up to you how you wish to do this, but basically all said and done here, you should be taking probably 6.3 times 10 to the negative 4, 0.238 over 0.251 should be the equation that you do, yes, solving for x. Oh wait, no, sorry, did I mess that up? No, I think that's okay, isn't it? And I think, let's see here, you get 5.97 times 10 to the negative 4, okay? And if you take the pH of that, negative log, okay, so the pH therefore is 3.224, I think. I'll stick with or I think it's 4. 3 significant digits just because there's 3 in the question, although on a diploma question you wouldn't be able to do that, of course. There's only 4 boxes, but so 3.22, that would take it up there. 3.224, so that's how you'd find the pH of that buffering system made with 2 different concentrations there. Okay, so that's how you would do that one. Good? Yes? Yep. That's what it started with. So that's what at equilibrium, that's what the concentration was. They don't have to be the same. Okay, that's what it says in there, right? You start it says calculate the pH of a buffer containing 0.238 molar HF and 0.251 molar sodium fluoride. So we're just worried about the fluoride, right? Because that's the base part of that. Okay. Let's look at this one. I want you guys to write this equation out, put the information in, same thing exactly. But here you have an NH4 plus and an N, sorry, yours is a little different. I don't know what happened here. I don't know how that got in there. That's what yours says there, yes? So I want you guys to look at that, NH4 plus NH3. That's its acid and the base that goes with it. And I want you to write this out appropriately. So this is what you're going to see here. You decide how you're going to write that out as perhaps an acid. If you really want to do the base, go ahead. I don't care. Maybe you can prove me wrong. Maybe it doesn't work out. I don't know. I think we'll be fine. You decide how you wish to write that out, though. I would strongly recommend you write it out as an acid. Okay? So it should be 0.175 molar NH4 plus and 0.175 molar NH3. Yeah, you have to assume it is. Yeah. Well, it's a buffer solution, so remember, it's anything that you, if you add a little bit, it's going to equal, yeah. Okay. Okay, let's go, guys. Come on, hurry up. So, if you want to write it out as an acid, of course, you probably should start with the acid because acids produce hydronium ions. The acid in this case, of course, is NH4 plus, aqueous. React it with water. Remember, has to be a proton donor, proton acceptor. H3O plus, aqueous, and NH3 is what you'll have left over. They told you this is 0.175 molar. This is 0.175 molar. Gee, maybe H3O plus is 0.175 molar. That's not, because it doesn't break up 100%, right? So the Ka in this case would be of course, H3O plus, which we don't know, 0.175 molar. For the NH3 here, of course, this would be your NH3 here, over our NH4 plus, which is 0.175 molar. That's your NH4 plus there. Okay, those two can cancel. So basically, your hydronium ion concentration is going to equal the dissociation or the ionization constant for this acid here, and the ionization constant for this here is. Actually, don't know. No, that's it. Yeah, 5.6 times 10 to the negative 10. Okay, and that, of course, will equal your hydronium ion concentration. Okay, negative log of that. So if you take the negative log of just that, you should be good. pH is 9.252. Yeah, 2. Okay. 9.252. Once again, you could have written it the other way with NH3 plus water gives you NH4 plus and hydroxide. Then you'd have to find the Kb value, find POH, and then find pH, which you'll get that. Just the opposite, right? So that's what you need to do for those buffer systems. Okay. All right. Keep in mind that when you're talking about this, like I said, if it asks you, here's some acetate ion, CH3CO minus, what are you going to react that with if you're going to be in a buffer system, right? Well, if you add water, you get, of course, H3O plus, right? Or not H3O plus, but the acid, conjugate acid of that. It's always acid and base go together, conjugate acids, conjugate bases, okay? We'll see about homework kind of thing, but I think you'll be fine. Just kind of think about it a little bit, and I'm sure you'll be fine there.